So we continue from the lectures of yesterday morning, and if you remember, we were discussing these plots as last things, in which I was showing the dependence on the energy of the collider of the production cross-section for different processes, and in solid line you have the VBF-induced processes, while in the dashed you have the direct production. So you see that with the increase of the energy, the VBF-induced production is becoming more and more the dominant one. Okay. Cross-section are growing. Cross-section are available also for the production of 3X. Also, this process can be studied, and they are the main production channels that lead you to high statistics for the production of the X and the possibility to probe the X with precision. Okay, so as was said, I think it was asked even in one of the questions yesterday. So you can get at the sub% precision, for example, with this kappa W, that is just parameterizing the interaction of the W with the X, because you're looking actually at this process, okay? And so this means that from the theoretical point of view, for modeling this kind of process, you need sub% precision, okay? For kappa Z is the similar things with the Z, we have less precision because the production cross-section is smaller, but for example, it can be increased and going down to like percent or even below percent at 10 TeV in some experimental setup in which you say, I have the Z boson fusion, I see this process, and I want to tag this muon that are going for. So you are sure that it's not only vector boson fusion, but also that it has a contribution from the Z. Okay, so this is also telling you that depending on the setup that you use, when you say vector boson fusion, sometimes you mean I just care to see inclusively a final state. I don't care about the outgoing particle like the muon or the neutrino, or you say I want to see the muon. And this is called typically in the literature the same vector boson fusion, but it can lead to different experimental setup and also different precision on the couplings. And you see there are several couplings that are going sub% level here for the X. And in all this coupling here, there's not the X self interaction. These are the important these are important parameters. This is actually, the trilinear and the quartic with the X. And it's precisely what discussed Hitoshi yesterday. So this is super relevant for describing the electroweak phase transition and the Higgs, the baryogenesis. And we often think that we know the potential of the X that has this form. That this is if we say, okay, standard model is the theory. But if we allow for modification of the X self-couplings, and then we probe directly this possible modification of the LHC, now the potential is actually in this in this band here. Okay. So all the lines that are going inside this band is the shape of the potential you could have. So obviously, I mean, you need to know it more precisely also to answer the question that Hitoshi discussed yesterday about electroweak phase transition. So you want to characterize really the potential of the X. So because what we know very well is the minimum where it's located, but not the shape. If you assume that, so not if you assume, if you let the possibility that there is physics beyond the standard model. And the precision that you could have at muon collider at 10 TeV is of the order of 3%, for example, so on the self-couplings. And so you can really then characterize the potential in a way that is more precise, much more precise than, for example, the results you could get at the high Lumi. LHC. Okay, so all these results that I discussed now about the precision, they relied a lot on this vector boson fusion process. So you may think, okay, we have direct production and vector boson fusion process. So the cross-section at high energy are much more, are much larger for vector boson fusion. So why do we really care about the direct production? So what is the gain of considering not only the vector boson fusion, also direct production that has cross-section that are typically smaller if you go to higher energy. So to do so, to explain you this, I'm going to do like a crash course in effective field theory. Okay, I'm trying to do a parallel with the past and try to let you understand why it's really important, this direct production. Because the key point is that in vector boson fusion, as I told you yesterday, let's take again the case of the top. For example, you could have W, X, top, or T bar, gamma, Z. As we said multiple times yesterday, these W here are carrying away a fraction of the momentum of the muon. So the energy that is entering here, square root of S hat, let's say, is smaller than the energy of the collider, while here the energy is the energy of the collider. So you're really probing hard interaction at a different scale. In one case it is the scale of the collider, in the other one is a scale that is much smaller. So to give you a parallel, so imagine now to take another process that is mu plus, mu minus, that is going into E plus, E minus. Okay, here you have a Z and a gamma. So if you plot the cross section as a function of square root of S, this has a shape like this. Okay, so this is the Z resonance. Okay, so your production cross section starts at around so at 2 times the mass of the muon. Yes, obviously, because you have to collide the two muons. It peaks at invariant mass that is of the order of mz here. Okay, let's call it small mz. And then it goes down again. So this is actually the part that is related to a QED. Here it's from the Z. And then there is an interference in the middle. But if you are in a region in which the muon invariant mass is much smaller than the mass of the Z, okay, so the propagator that you have here, that is like 1 over S minus mz squared, you can write it like just 1 over minus mz squared, okay? Because here is entering the momenta, so he's entering the invariant mass of mu, and you know this is invariant mass of mu, or the invariant mass, or this is equal to the invariant mass also of E plus E minus at leading order is equal to S, and is much smaller than mz. Okay, so it means that the momenta that is going around here, let's call it P, is irrelevant. Okay, so you can just write the mass of the Z. So what does it mean, this in practice? That in the standard model, your interaction would be L interaction uguale SC Z mu J mu Z with J Z equal J3 minus square M. J. So this is just a short version for saying sine of theta, theta weak and cosine of theta weak. So I just write S and C for brevity. And this is just the interaction of the Z, and this is the current that interacts with the Z that you can divide in a component that is the QED component. That is the same of the QED component that interact with the photon. Okay. And a component that is instead just interacting with the Z, that is the left-handed one. Okay, so this interaction is precisely giving you the interaction with the Z, with the, for example, E plus, E minus, or also Mu plus, Mu minus. Okay, so if you are in a region in which you are here, okay, so much below the energy of the mass of the Z, you don't really care about this momenta here, this propagator here. So you can imagine to go directly to a 4-fermion operator, okay, in which you are so you have 2 times this interaction, you are shrinking the propagator, okay. And so you can write an interaction that is an effective interaction here, well, 1 minus 4 GF square root of 2 Z, J, Z, we put it up, squared. Okay, so this is actually, again, the Fermi model. The Fermi model in which I just selected the current that I cared for this process here. Okay, there are also charged current, but for the example that we have here, we don't care. So you can easily identify so what is saying this? It's saying that if you go to very small invariant mass, the standard model can be very well described by the QED plus this other interaction that you have here, and the connection between the two models to matches this relation that we have here. So imagine you are a particle physicist of decades ago, okay? You know QED, but you don't know weak interaction, okay? And you're going to measure this distribution here, but you don't have a collider that arrive up to here. You have a collider that is just arriving at this energy. So your prediction of QED is actually something that is doing like this. Okay? So this is your QED prediction, where instead of S minus mz square, you just have 1 over S. Okay, so your cross-section is also going down 1 over S. So what you're going to do is measuring precisely this quantity here, okay, to see the deviation. Okay. So what's happening now? I'm getting lost in my, wait a second. 34. Okay. So now your prediction is the following. You have sigma of mu plus, mu minus, that goes to E plus, E minus, that is equal to the cross-section via the photon plus something else that you can parameterize like A GF plus B GF squared S. Okay? So you know that this quantity is scaling like 1 over S. It's easy to understand why also, because it has to have the units of a cross-section, and 1 over S is the unit of a cross-section. The only other scale that you have in the process are the mass of the muon, the mass of the electron, but you can neglect them, okay? And you also know that if you have a Lagrangian that has the Lagrange is always dimension 4, okay? So this current here has dimension 6 because you have 4 fermion. So also this GF has a dimension, the same dimension of 1 over S. So both GF and 1 over S are of the order you can imagine, GV to the minus 2, okay? So what are this A? Well, you can imagine that A are just the coefficient, general coefficient you have to calculate that is coming from the interference of the QED diagrams with the one with effective field theory. So it will be proportional to GF, okay? And this will have a dependence that is larger. It has a larger dependence on S, okay? So if you have then instead just the diagram that is this one squared, it will give you the GF squared dependence, okay? But it's easy to see that since this has a dimension 1 over S, this will be 1 over S squared. And so you need to have another term S here that is compensating to have the correct dimension and going like 1 over S. This is just a dimensional analysis. So you can understand that you get something that is going like 1 over S, something that is growing like S, and the interference that is like a constant. Okay, so what can you do? You can measure very precisely here. Okay, so if you are in a region that is in which this contribution is very small, you will determine via the calculation of all this quantity and the measurement the quantity GF. Okay, obviously, then once you have this model and you plug it inside here, you're not going to get the resonance of the Z. You're just going to get something that is going correctly here and at some point is departing and growing completely with the energy. But at least you're measuring effectively this interaction, okay? And you can imagine that this interaction that you have here, okay, this GF, you could write it also like C over lambda squared, where C is a coefficient, and this is, that is a dimensional, your new physics scale. Well, if you do so, and you do the measurements, what you get is that GF is equal 1.166 10 to the minus 5 GV to the minus 2. So this is telling you if I have interaction of order 1, this is equal of 1 over 240 GV squared. So actually, you didn't look at the peak of the Z. You looked like at the tiny deviation that you have there, and you measure a quantity that is telling you, look, it's very likely that there is something that is happening at this new scale, and the new scale that you see here, you know, is the round about the electroweak scale, because I mean the VEV, the W, the Z are all at the order of 100 GV. Okay. So okay, in this case we could do everything in a clean way because we know already what was the answer, because we know that the standard model was the answer. We were doing the effective field theory, knowing what was the correct answer. We are actually in the opposite situation now, because we know that there is physics beyond the standard model. We don't have a clear indication like in the other colliders before, where was the energy where you would expect new effects. But you can use an analogous language to parameterize possible deviation from new physics that is heavy. And this is exactly the idea that you have behind the SMEFT, okay, the standard model effective field theory. So you have a theory in which you use the same particle contact, that is standard model. There is some new physics, like here, there is not anymore the physics, the electroweak interaction, it's some new physics that you describe with the scale lambda. It works only if the energy that you are probing is smaller than lambda. So for example, if you want to do this story now, a 10 TeV collider, this language works if the new physics is above 10 TeV, or would work in some, if you look at the particular distribution, only if they probe energy that are smaller than the energy of the collider. And we can see a similar example, okay? So now imagine this is just an example. You can build many EFT operators, but imagine now that you have a new EFT operator that inducing, just to coming back to our process, mu tt mu tt c over lambda squared. Okay. Now, in an analogous way to what we saw before, this will induce a new physics contribution, mu plus, mu minus, in t bar, that is of the order of some coefficient, again, c over lambda squared plus b c lambda squared, c squared lambda to the fourth s. Okay? And your cross section will be equal to cross section of the standard model plus the cross section of new physics. Okay? Now, you remember I said, the QED cross section is going down like 1 over s. Then there is a peak. But then again, it goes down as a 1 over s. So if you see, after you surpass the peak of the z, again, it's going down. And similarly, in the standard model, the cross-section, as we said also several times, is going down. It's going down like 1 over s, okay? So now, you can actually say that this sigma standard model is equal to sigma bar SM over S, okay, just to have a normalization, okay. So now imagine that you have, you do some measurements. You do the same story of the hypothetical physicist of decades ago that doesn't know that Z, okay? But now for the new physics. You do the measurements and you find that the deviation you see at 10 TeV, that it means the ratio between the new physics effect and your prediction in the standard model is of the order of 1%, so 0.01, okay? So this, you can write it as C over lambda squared 10 TeV squared over sigma at SM. For simplicity here, I just put this A equal to 1, but you can put inside A and repeat the same arguments. So say, well, okay, good. I have this process here. I had, I can either, if you see some new physics, you identified some information here. If instead you don't see anything, you put a bound, okay? Now the question is, what would have been the precision that you would have needed if your energy, instead of being 10 TeV, would have been of the order of 100 GV, okay? 100 GV, okay, exactly 100 GV with TT bar, you cannot do it, but just to make the comparison simple. Okay, you say, okay, let's imagine delta 100 GV is equal, the same formula as before, C over lambda square, 100 GV squared over sigma hat standard model, okay? But this is equal precisely to 0.01 GV squared over 10 TV squared. So is equal to 10 to the minus 6. So what is the message here? That it's true. I mean, these processes that are direct production have lower cross section. Okay, they have a lower cross section, so there are less events. But in some cases, if you parameterize new physics, for example, in this EFT way, you gain in the sensitivity of the cross section with the energy. So what is happening now is that this direct production has a growth with the energy of the dependence of new physics interaction that is much larger than than the case of the standard model. So the gain that you get with the energy is impressive, and so you would have needed at like 100 GV scale 10 to the minus 6. Okay, if you instead of having 100 GV you have 1 TV, you have 10 to the minus 4. And the challenges that you have to do for precision physics at 10 to the minus 6, at 10 to the minus 4, at 10 to the minus 2, they are different. Okay. This is the big difference. And so this is an example of like how you can gain with the gain on the sensitivity of new physics with the energy. So these are two different ways. And another important points to keep in mind. I mean, I'm stealing the plot from the people in the first row. Here is that you also have that the luminosity is also scaling, is increasing with the energy at the Muon collider. So it's true that the events, so that cross-section are dropping down with the energy, but for example, a collider that you're increasing the energy, the luminosity scale of the machine is compensating for the decrease of this cross-section. So the number of events, we are still speaking of events that, for example, for Muon TT bar, we are speaking about order of 10 to the 4 events. So is a region where you can do actually studies that go to the that can potentially go to the percent level. Okay, so now in the last part of the lecture, I want to also go to the discussion of the electroweak. Is it clear this part before I change topic? Don't know if you want to comment. You propose this kind of ideas, so this is why if you want to comment. Yes. Mm-hmm. Mm-hmm. You're sorry, you're yes, yes. No, because I mean, in this discussion that I did here, if you see, I focused on a process that precisely is the direct production, where in the first approximation you can also forget about the PDF description because it's the muon in the muon. Okay, so we are not so there are correction to it, but the bulk of events are precisely the energy of the collider. The mm-hmm. No, it's different. I mean, what you gain a lot in this discussion is the direct production, because if you go, the gluon-gluon would be the equivalent here at Muon collider of the VBF induced. Okay, with the VBF induced, you can also have interesting things, but it's more subtle, obviously. So the discussion is there is an interplay, obviously, with the power growth in the matrix element. Okay, and the fact that if you go to higher invariant mass, you have lower events. So you have to combine the two things. Now, I don't understand exactly what is your question, but one is modeling how you treat the process, the VBF induced process. The other one is within the hard process, how you model the EFT interaction. Okay. I think still has to be explored in the EFT context. So I mean, people started now to explore how good is the PDF description versus matrix element for the standard model itself. Analysis of comparison of these two modeling for EFT process, something that is interesting to do, but is still to be explored, I have to say, because you are combining two different problems. Then also, I have to mention that not all the EFT modification leads to growth in the energy. So this is an example, but for example, the one that are modifying, for example, the trilinear X self-coupling, so the one that mentioned yesterday also Hitoshi, that you add, for example, phi daga phi to the third C over lambda squared. This operator here is inducing a modification of the trilinear and the quartic X-self interaction, but it's not leading to a growing, directly a growing the energy. And so you probe it not with this direct production process, but you probe it directly with the vector boson fusion. Other coefficients to the trilinear are different. So here I gave like clean example that gives you so it's to give you an understanding of the potential. Then when you consider different EFT operator, different processes, there are many things that are entering into play. You have to, I mean, the end of this, one important message also that I want that you can get from this lecture is that you can reason a bit with these logs, these things, but if you want to do precise prediction, you have to do the calculation. After having an intuition, you have to calculate it, and you have to do it in the best accuracy that you can have. So now we'll move to the case of the electroweak correction, and I want to make a point that is very clear at the beginning, because electroweak correction is used in different contexts, also in collider physics. In general, they mean NLO electroweak is order alpha electroweak correction to some quantity. Can be a parameter, can be a cross section, and electroweak correction can be also higher power of this kind of correction. And in E plus E minus physics, they have been paramount. I mean, they really proved the standard model as a quantum field theory. So the classical example that I want to give you for precision physics at the plus and minus is the fact that if you take a standard model, you can write the mass of the W as EV2 sin theta W. Okay, and if you remember, at the beginning of the lecture yesterday, I said that there are 18 parameters of the standard model. You can have infinite prediction. For the electroweak sector, for the gauge sector, there are 3 parameters. Okay, so if you measure this quantity, you can predict MW. Then you measure MW, you should see that if the model is consistent. So for example, you can measure E, and this you get it precisely from the electromagnetic dipole moment, and this you get something at the order of precision 10 to the minus 10. You can measure the V, okay, how? Well, GF is actually equal to 1 over square root of 2 V squared. So if you measure precisely the decay of the muon, you measure precisely V. So the position of the minimum of the potential, the VEV, we know it since decades. Okay, since you saw the decay of the muon, so Fermi model, you can get directly the value of the V. Okay, and this also has something of the order of 10 to the minus 6 as an error. And then you can infer sen theta from the mass of the Z, okay? Because this one can be rewritten like EV to SC, and so that goes to S squared 1 minus S squared equal to pi alpha square root of 2 GF mz squared. So what you do, you measure mz, you already measured GF, you measure E that is giving you alpha, you extract S, and also you get this at very good accuracy. Now, then you go to measure MW, you plug the relation that you have inside here, and your value of MW is 40 sigma away from your prediction. Not a bit, 40 sigma, okay? So, because if you have a precision of like the order of plus minus 10 to 15 MeV on MW, and you plug this, you are 40 sigma that is away. Why? Because in reality, you should have taken into account an electroweak correction to this quantity. So the fact that there are loops like this one, also loop like this one, okay? So in fact, the mass of the W is a different thing. The mass of the W is the mass of the W at leading order, that is what I've written here, 1 plus alpha, so the electroweak coupling, and then some coefficient that multiply mass of the top squared and Z squared plus B log mh squared C mz squared. So what is telling you this this equation here? Well, actually, in order to get the right prediction of MW that is compatible with the data, you have to take into account loop effect that depend on the mass of the top and on the mass of the X. This is actually, I mean, how before the top was discovered, you could infer the mass of the top. When the top was discovered, the precision of the mass of the top was lower than the information that you had from this relation. Okay, nowadays no. Okay, but this was also a way to put constraint on the mass of the X before the. So you can understand that you can play the same game, adding inside the loops also some new physics interaction. You look at this relation, and you put constraint on the new physics. Okay. And if you take an E plus E minus collider like FCCE, the prediction that you can have on the mass of the W, so delta M W can go below the 1 MeV. Okay, so we are speaking about a 10 to the minus 5 error on the mass of the W. So we are really probing with high precision this relation. So we're speaking about effects that are at the level of 10 to the minus 5 that are, you know, the same, you see, this is the physics of like low energy A plus A minus collider. You want to probe new physics, you have sensitivity by super high precision, okay? And when you want to have under control these effects, there are important things like correction like next to leading order, description of the PDF in a very accurate way. And this is not what I'm going to speak about today, okay? This is super relevant, okay? But I don't want to focus on this because in the actually muon collider, you have other effects that are coming from the electric correction, as I said, that are much, much larger than these problems related to the 10 to the minus 4 or 10 to the minus 5. You have this so-called electroweak Sudakov log. So to explain you how they emerge, these large effects, I'm giving you again another crash course now in what is the structure of a next to leading order calculation, okay? So we go back again to our friend, the TT bar production, that now you should know very well. So a leading order in a PP collider, this is order of alpha squared, the cross section. And you get it from two kind of process, TT bar and gluon to TT bar, in which you have, in one case, diagram like this one, and in one case, diagram like this one. You see, you have GS, GS, okay, and similarly here. So the amplitude is scaling like GS squared that is proportional to alpha S, and the amplitude squared is scaling like alpha S squared, okay? The same here. So what is NLO QCD? NLO QCD means alpha S correction to leading order, okay? So leading order means that you have, for example, the partonic cross section is order alpha S squared. For example, let's take the case of QQ bar to TT bar. This is proportional to the amplitude Q bar 3, as I said, is of the order of alpha S squared. Okay, so NLO QCD, what do you have? You start again with the same process and QQ bar in TT bar. You have a diagram like this one, loop, okay? So for example, this is M QQ bar, one loop. So this has GS, 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 GS. So this is the amplitude is proportional to alpha S squared. So I cannot square this amplitude to get NLO, because if I square this amplitude, I get alpha S to the fourth, okay? So actually, the sigma alpha S to the third for Q bar to TT bar is 2 times the real part of MQQ bar 3 times MQQ bar conjugate loop. Okay? So you are getting what is called the virtual correction from the interference of this amplitude that includes these diagrams, also many others, and this other one. And similarly, you get it for the gluon. You will have other diagrams, for example, any other kind of topology, like this one. You do the interference with this one. Is that all? No. Because when we speak about NLO correction to some prediction of a production cross-section, we are inclusive. So what we mean is like, what is the NLO correction? So we start with the production of TT bar. We say, what is the NLO correction to the production of TT bar plus something else, okay? This is crucial. So if you want to say this, at the same order, you can have other contribution that are not only the virtual contribution, but they are so-called the real correction, okay? real correction can be QQ bar that goes in TT bar plus a gluon. So for example, this one. Also, gluon to TT bar plus a gluon. So, but also gluon, quark or anti-quark that goes to TT bar plus a quark or anti-quark. So now, okay. So if you see here, you have 1, 2, 3, GS, GS, GS. So now, if you get M is a 3-level amplitude for QQ to TTG, you have that this amplitude squared is proportional to alpha S to the third. So the NLO QCD correction are actually a combination of loop correction to the case in which I don't emit a gluon and 3-level effects in which I emit a gluon or a quark. And if you look at this diagram here, maybe not particularly these diagrams, but the class of diagrams that you have here with the loop, these are ultraviolet divergent, so you need to renormalize them, you can perform renormalization, and also infrared divergent. When you hear infrared divergent, it means that there are some condition in which the gluon inside this loop is soft or collinear of the particle that is giving you an infinite. And this is precisely the reason why you cannot say, let's calculate at NLO what is the cross-section of producing 2 tops and nothing else. This is impossible. It's also experimentally not possible because you could never say at the experimental level I produce 2 tops and nothing else, because you have some granularity of your detector or minima. You can always allow for something that is being emitted, and also a clear sign is that your cross section would be infinite, minus infinite, so it's a bad sign. Instead, what is happening that also these other diagrams have infrared singularities. And when you combine everything together, the infrared singularity disappear, you get a finite prediction. So this is actually what is also known as the KLN theorem, okay? So if you are inclusive, automatically this infrared divergence cancel, and you get the right prediction. Now, what is happening at 2E plus and minus? Plus and minus, for example, if we start with the typical process that is, I mean, we can start again with the TT bar production. You can imagine to look not at QCD correction, but to electroweak correction. You can also look at electroweak correction at proton-proton collider, obviously, but it's a bit more complicated. And so now you go to E plus, E minus, and you go to NLO electroweak. So what is happening? Now I'm exchanging, with the case of before, alpha S with alpha. Then the quark with the plus or the minus, and the gluon with the photon. And we have the same story, okay? We have E plus, E minus that goes into TT bar, photon that is going to TT bar. In one case, you have photon Z, TT bar, and then there can be loop, okay? For example, W, T, T bar, B, neutrino, E, E. I can have photon, as I said. And then here I have, I don't know, the X here, the photon, the top. And similarly, I have then, you know, here I had the cuckoo bar to TT bar quark. I will have E plus E minus to TT bar photon. And similar, the same, exchanging every time the quark with the electron and the photon with the gluon. Okay. So you see that there is already something different with the QCD case. Why? Because in the QCD we had interaction that were strong interaction, which there was one vectorial massless particle, that was the gluon, and it was the one that was inducing the infrared singularities. Here we have one that is inducing the infrared singularities, that is the photon, and this is the reason why I'm looking at E plus E minus TT bar photon, or photon E plus to TT bar E plus, because I have the same problem. I have UV divergences, and to have the renormalization, I have to take into account all the standard model, because you see I have the W, I have the X, I have all the particle content of the standard model. But to regularize the infrared divergence, I care only about the QED part. Okay, so the electroweak is split in two: a weak component and a QED component, and only the QED part is the one that is leading to the to the infrared singularity. Plus, if you look at it, since only the QED part is necessary, okay, I don't have here in the process with the real radiation TT bar plus Z. Okay, I could have it, but could also not have it. So the fact that I want to calculate the cross section at the low electroweak level of the production of top quark pair inclusively, it's important that you are inclusive on a photon. Okay, because at the experimental level, you can distinguish if there is or there is not a Z in principle. Okay, you can. It's not like a photon that can be infinitely soft. A Z is there, is producing an effect. So in principle, if you had a 4 pi coverage of your detector, you can always see a Z that is decaying. Okay, so I don't need to put it here. I can, but I don't need. Okay, so now if you want to regularize these diagrams, what is happening? A technical way to do it, okay, but it's helping you in understanding what is the problem, is saying that you introduce a fictitious mass for the photon, okay? This fictitious mass of the photon is leading you to a regulator for the soft soft divergence. So you introduce a mass of the photon, okay, and you keep the mass of the electron in your calculation, and you will see that loop goes like minus log n s hat over m squared, where n can be equal 1 or 2, and m can be the mass of the photon or the mass of the electron, and the real proportional to log to the n, the energy squared of the photon that is emitted, and the mass here. So what you see here is that if you send this regulator to 0, you independently have loop that diverge and reals that diverge. Okay, here also n equal 1 or 2. But if you combine them consistently, you get that loop plus real will lead you to some things that are, some logs that are of the form energy of the square root of s, where energy is the energy of the photon that is emitted. So if you don't put a cut on the energy of the photon, the photon can in principle span all the possible energy, and you eliminate your divergences. Okay. So this is telling you that in QCD you don't have these logs, in QED you don't have it. what about the electroweak, the weak part? Because the point is that in the weak part is the same story for the loop, okay? In the loop, the virtual have again these logs, okay? So the virtual contains these logs that are negative, as I said before. Now they depend not on alpha, like the, okay, I didn't write it there, but in QED they're proportional to alpha, but alpha sin theta squared. And then there is log, again, n of s hat over mv squared. Now the regulator is the mass of the vector boson, okay, with n equal 1 or 2. And the real, so you expect that the real are cancelling this log. Well, it's a bit of a problem, the real. Why? Well, imagine now we are again at E plus, E minus collider that is going to TT bar with the energy that is just above 2 times the mass of the top. Okay. You can have this log, this diagram. Okay. But you cannot have a diagram in which you emit a W. Okay. Because it's violating clearly the charge conservation. So you have something that is neutral. You cannot go to TTW. The only way would be having a neutrino in the initial state, but neutrino in the initial state for low energy, we cannot have it. So the equivalent real emission diagram to this one, you cannot do it. Okay. Then imagine now you have, instead of the W, the Z. Well, this is true. You can do it because you go to E plus, E minus, to TT bar Z. Okay? It's possible. But if your energy is just above the TT bar, you cannot produce also a Z. So you see, as soon as you have 1 electron volt more than 2 times the mass of the top, or even less, you can produce a photon. But to produce a Z, you need at least the mass of the Z, energy more. So the real will not be there. So the real difference between that I want to appreciate between always this loop and real contribution is that in the electroweak sector, it's not mandatory to add the radiation of the Z over the W. And typically, if you look at the literature and you take a paper and you say, we calculate an electroweak correction, there is never the contribution of this. Or if there is, it's stated precisely why they do it and they motivate it. But it's not mandatory to do it, okay? And so what is happening? That if you don't take into account this real radiation, okay, you're left with this log. These log are there. And they're there, and you can understand already that if this S is going to the energy of a 10 TeV muon collider, and these are log squared, these are large log, okay? It's true that if you increase the energy, also of your muon collider, you will have the possibility to emit this Z boson. And similarly, at LHC, you have 14 TeV, so you can clearly emit a Z boson. Well, at LHC, there is another problem that you have to make to compete something that is TT bar with TT bar Z, so the invariant mass is minimum, at least a bit larger than what you have a leading order. You have to convolute it with the PDF. The PDF dropped down incredibly, so you pay a price of the PDF. Okay. So, for example, let me see if I have it in the slide here. This is exactly the case of the PT of the TT bar production at LHC. what you see here are exactly the Sudakov log. So if you go to larger PT, electroweak correction increase, they arrive like of the order of minus 30% at this 3TV PT. This is the logs that I just written there. And then you can say, okay, this is the log, but what if I take into account also the emission of a Z, an emission of a W, because at the LHC I can do it. Instead of taking UU bar, I take UD plus a W. But this is the emission of the additional Z, W, or X. There is a log that is growing, but it's only mildly compensating this effect. Why this? Because this KLN theorem that I mentioned before relied on an important thing. So when you do QCD calculation, you look at the top, you don't look at a green, a red, or a blue top. You look at the top. You sum over the color index, okay? So the color indexes, what is the equivalent of the color indexes? So the color indexes are in a SU3 model. In the electroweak, you have SU2 in the weak part. What is the equivalent of summing over the color in SU3 for the SU2? That would be summing over the component of the doublet. But typically, you don't say, I look either a muon or a neutrino. I look either a top or either a bottom. You are choosing a top, not the top and the bottom. So you are not summing over the component. So even if the energy would be super large, if you choose a definite particle, you don't have the cancellation of the log. So this log, they are there. They remain there, even if you are inclusive over the radiation, okay? This is an important point to keep in mind. And there is also a big difference of the Muon collider with the with the PP collider. It's that here we see this this effect of the Sudakov logarithm that are becoming quite large, but this is in the region in which is the tail of the distribution. So not where you have many events. Okay, so large PT means at LHC few events. They can be very large, even minus 50%, and they are used in the analysis already now, for example, in WW production, but it's not the bulk of the event. So where the cross-section is large, electroweak correction are percent level. So because in general, it has always been like this. Electroweak correction deals with percent correction. So it's precision physics. At the Muon collider is a different story, because if you remember, the spectrum in TT bar production of MTT is like this. Okay, so if you are staying here, you are like an E plus E minus machine that is at low energy, but you are at a high energy here, and so you are the Sudakov logs are large here where you have many events. So we are speaking about effects of tens of percents, not in the tail of the distribution, but in a large part of the events. And this is exactly the region where I told you that you can exploit the precision physics to put constraint on the EFT operator that grow. So it means very good idea. We use that, this idea that you have a grow with the energy, we exploit the sensitivity, but we have the problem that the standard model is receiving large correction. And so if the standard model is receiving large correction, you have to have under control. It's also signaling one important fact that if at NLO you get corrections that are of the order of tens of percent, and you want to have a percent accuracy, you have to go even to higher order. Okay. So before looking at the results, I want also to stress a point. So you look at this the structure here, and I've written where it is. The log can be power 1 or power 2. Okay, so a squared or linear log. Also here. So is the double log enough? So is the Muon collider at energies in which in first approximation I can say I calculate just the double log? No, the answer is no. And you can do this in a plot in which you are just plotting. Here order 1, I'm just mentioning the prefactor without the log that you have typically in the correction. Then you plot the single log and then the double log. like solid line, and then you plot the same quantity multiplied by 10. Why multiply that by 10? Well, because if you calculate exactly what are the results, you typically see that in front of this log, this L minus that appear here are single log, there can be coefficient like 8, 14, and maybe in front of the double log that are here like 2 or 4. So it's true that there are the log, but there are also some coefficient. And you easily see that at the energy up to 10 TeV, single and double log can be of the same size. So if you just take into account the double log, you can miss important contribution. So the first information is logs are important, but single and double are important. Another interesting things to notice, I don't want to go into the detail of this slide, but it's telling you what? That when you calculate the electroweak Sudakov log, it's simpler the structure because you don't have to really calculate an actual loop. What you care is about log, coefficient, and three-level matrix S. So you can approximate the high energy contribution of these loops as three-level diagrams times logs times coefficient. But the interesting thing is that, for example, if you take a diagram, let me see, like this one, okay, to write the log that you have here, you will need the amplitude neutrino E W T B. So it's like you're saying, I take this amplitude here and I multiply by a log. Okay, so you can write it as this, and actually is a bit more complex. This is the easy way to explain it, but this is also saying that inside this log you can have not only the energy of the collider, but also all the possible invariants. So for example, in a 2-2 process, there can be T, U, so all the Mandelstam variables. Okay, and now the slides that I want to show are results for the Muon collider, in which we care only about this part here of the spectrum. Okay, so what I'm doing, I'm saying, okay, I want to produce TT bar production, and I ask that the mass of the TT bar is larger than 0.8 square root of S, the energy of the collider. So this is telling you that you are in this region here, in which you can completely neglect all the vector boson fusion, neglect the PDF of the photon, of the W, of the Z, looking at the results. And then there are some cuts that are like minimal cuts, like minimum PTO 100 GeV, some reasonable eta in distance, and see what are the effects. Okay, now the spectrum of the PT of the top, you see, is completely different from the one of the that we see at the LHC. At the LHC, started here and dropped down. Here, it's starting at the maximum energy, and it's going down. And the size of the electroweak correction is this line orange here, that is covered by the red one, and is at 3 TeV, quite flat. Also, it's not, before we saw that the electroweak correction were growing with large PT, here are quite flat. Why? Because even if you're moving the PT, S is always of the order of the energy of the collider, because you asked that is at least larger than 0.8, and in fact, asking that is typically equal to the energy of the collider. So there is always the large log of the S. So you have a correction order of 30% over the full spectrum, and at 10 TeV of the order of like minus 50%. And the orange and the red are NLO, the orange, so the complete calculation, and red is just these logs. And you see that these logs are catching the NLO correction at the percent level. So this is really, if you remove this log, you find the size of the NLO electroweak correction that are the ones that you typically see at the plus and minus collider, at LHC not in the tail, so the percent level. But there are also these logs that are really a large part of the contribution. Okay, but can be even worse. So if you take this process like ZZ production, you go to 100 TeV, correction here are, you see here, in this peak here, they are minus 120%. So if you have a correction that is minus 120%, it means that your cross-section is becoming negative, okay? Obviously, negative cross-section, there's something wrong going on, because I mean, there's no physical meaning for a negative cross-section. This is just a signal that your perturbation theory is breaking, okay? Because if you have like an exponent that is going like minus alpha to the x, and you say alpha is very small, so I write it like 1 minus alpha x plus, but then x is larger than 1 over alpha, and you take this quantity, this doesn't make any sense. It is exactly what is happening. We say, oh, alpha electroweak is a small parameter. We do the NLO electroweak, calculate NLO electroweak correction. The problem then in front of alpha, there are these logs. These logs are exploding, and they're giving you negative correction. So it's telling you that an NLO electroweak is not helping you in precision. It's giving you completely unreasonable results, and you have to go to the next level, that is resumming the tower of the log. So you calculated this one, but in reality what you need is this one. So you would need to resum all the things that are here, okay? And so this, for example, if you do it here, that you see that your cross-section leading order was like this. You calculate an NLO electroweak to get precision. You get negative cross-section, you resum the log, you jump up here, and this is telling you something important, that an NLO electroweak cannot be neglected, but destroy your cross-section. You have to take into account the resummation, and the resummation is reducing a lot the events. So we are at the level in which we want to look at a process. We want to have precision, and we do resummation, not because we need it for the precision, just because we need it for reasonable description of the process itself. Can you draw the conclusion that you always need this resummation? No, because we just saw the example before that in TT bar this was not happening. So this is also telling you an important point. When I was saying last time, the challenges, the list of challenges, we have to explore it, because you cannot take an example and draw the conclusion that is the same for all the processes. Because for this TT bar, they are large cross-section, but they are not exploding. Here they are. So in some cases you need the resummation, in some cases you don't, but you have these electric correction that are giant, and we are not used to this effect. Then you can play again the game and say, let's take into account also the emission of the Z or the X. You are dominated by the emission of the Z, but for example, if you look at the PT of the top, again, I'm plotting here the effect of the electroweak Sudakov logarithm from the virtual, and then inclusively I take into account the emission of the Z or the X. Yes, it's giving a contribution, but it's super tiny. So you don't have, so if you include also the emission, this is a 3 TV, this is a 10, you have a compensation. There are these logs, but they are very small. So you are still left with minus 50% correction here. But you see that, for example, if you relax a bit this requirement that we had to say, I want the invariant mass to be larger than 0.8 of TT bar, I say I just wanted to have larger than half of the energy of the collider, you leave more space for the additional Z or X to be radiated, and you see that, for example, here, the emission of the heavy boson radiation is giving you larger effect. The only case in which you really see large effect is if you plot in the invariant mass distribution. Because now, if you plot in the invariant mass distribution, the story is different, because here you are dominated completely by the PDF at leading order. Instead, you can have, with the emission of the Z, that if you go to small invariant mass of the TT bar, you leave a lot of space for the Z to be emitted, and you see this large cross-section. And for example, I think that yesterday there was a question about the valley. What we can do in the valley, we can see some new physics. At least this is part of the valley, because it's just taking one part of it. And you see that, for example, what we have here in the spectrum of MTT is taking into account inclusively the real emission of the Z can be important. And now I want to show you some plots related to the effective weak boson approximation. Okay, so I want to make you notice that if now we want to consider the full spectrum, okay, we have to consider also the vector boson fusion processes. Vector boson fusion processes, as we said, they are things of this level in which you can either describe it as a full VBF or vector boson times the PDFs. Okay, here. So if you do it in this way, they are processes of the order alpha to the fourth. So they enter at NNLO electroweak formally, because their correction that are order alpha squared times the leading order. That is the process you would have with the E plus E minus. If you do in this way, they're instead of order alpha squared. So this is also telling you that you use the PDF, you use the full matrix element, in your perturbative expansion, they're entering at a different level. Okay. So here I'm taking the comparison like calculating ZZ to TT bar versus the matrix element. I removed Q e D from mu plus mu minus to TT bar mu plus mu minus. And I try to do a comparison. So I'm plotting the ratio of what you get with the EWA and the full calculation. Well, here is the invariant mass distribution of TT bar is pretty okay for small invariant mass. Then it doesn't work anymore, but this is what you are expecting, because the EWA is working especially if the invariant mass of the object is produced is small. But then you see that it starts to have other problems if you go to other distributions. So for example, the pseudo rapidity of the top or the transverse momentum of the top. So you really see there is a discrepancy between the effective weak boson approximation and the matrix element. Still, you can say that at least for this distribution, it's working pretty well if you set a scale, although moving the scale will give you an uncertainty that is of tens of percent. A different story is, for example, for WW. If you do WW to WW, you are completely off. So this plot on the right is on a log scale. It's not on a linear scale. So you're seeing that, for example, the same calculation done with the EWA or with the matrix element, it's giving you completely different results. Okay, so since I have 10 minutes left, so I don't have so much time to discuss the rest, I will try to go a bit faster, but the main point I want to make here is that, this is telling you, okay, good. If I do this description in general with the EWA, it's giving you a good sense of the fact that this muon collider is like a vector-vector collider. But is it really the best we can do for doing to getting the precision? These plots we have here tell us that probably, for the sake of precision, this is not the good approach. So what we did, we recently put out this paper in which we presented a framework in which you can do NLO electroweak corrections and combine these diagrams that you have here together with the NLO electroweak correction that formally would be part of the next to next to ring or electroweak, but they are very much enhanced because these are the VBF contribution. And in doing so, what do? We keep the PDF if there is a photon, but not if it is a Z or a W. Okay. And the results that we found, they are quite surprising, I have to say. Because first of all, I show you this, then I have some zooms, but you see these are exactly the spectrum that we discussed many times. This is for the case of TT bar, these are 3 TV, and this is a 10 TV. And you see that a 3 TV looks more an E plus E minus collider and less a proton collider, proton-proton collider, and at 10, the dominant effects are here in the left, that is a proton-proton collider. And the same story is here in WW production. So here are just the 10 TV zoomed. Okay, there are many plots, many lines here, but look, we are speaking about in this distribution. In the left, if you assume 10 inverse afterburn of accumulated luminosity, 10 to the 5 events per bin, here 10 to the 7 events per bin, and in the valley here we're still at the level of hundreds of events per bin. Okay, and we have the direct production here, and instead here the vector boson fusion production. But we have, if you are inclusive, the two processes enter together and they merge, and you have a smooth transition to them. Okay, and at the same time, you see important other effects, like for example, here you see this green line is the effect of the Sudakov logarithms that are happening here and also here that you see for the WW that are becoming large in the right. And the effect that you see here on the left are again large effects of an electroweak that I could not discuss today in detail, but they are all related instead for the multiple emission of photon and the interplay that you have from the different initial state. Then it is also shown the emission, for example, in this plot, there are these other dots here that is, for example, mu plus, mu minus to TT bar, nu, nu. So what is included in the W fusion process. But actually, this is including also, for example, some diagrams that have TTZ with the Z that is decaying into neutrinos. So in fact, this blue line has a shape that is the one of the WWVBF induced TT bar, and then it's going up again because actually it's starting to get dominated to TT bar Z that we, for reference, reported here. But the main message of this plot is that if you want to look at the full spectrum, many effects are entering in the game. There is all the story of the Sudakov log on the right, and there are other things that, for example, are related to the PDF in QED that I also could not describe, but if you start to do a variation of the factorization. So you remember in the first lecture I said there is this quantity that is the factorization scale. Factorization scale, in principle, we should not have a dependence on the factorization scale because the prediction do not depend if you knew everything precisely, but we do perturbation theory, so we can vary to estimate the uncertainty. So here on the left, we have that at leading order, the variation of the factorization scale of just the PDF is giving you 20% effect. You cannot have 20% uncertainty in the bins with 10 to the 5 events, 10 to the 7 events, and then use it for the precision. This is just from the variation of the scale. You go to NLO electroweak, you still have 10% of variation, but if you include just these diagrams here and correction with the ADN NLO, you reduce incredibly the scale uncertainty of the PDF. So this is telling you have to go to higher order, not only to get the jump in the prediction, but also the uncertainty that you have there. So all these effects have to be taken into account. They are new, they are unexplored, okay? And I think that it's a really exciting field. I have to say, I want to remark this again, because not only the potential for new physics of a muon collider is incredible, But also the challenge in the modeling of the process from simply a standard model point of view is very interesting. And last but not least, so this I want just to give you as a final point that people really just started to take into account this, is that if these effects are at minus 100% level or tens of percent that are coming from electroweak interaction, they will be there also if you have a BSM signal. If your BSM signal is electroweak interacting, you will also get this correction. So it's telling you also that new physics typically concern the electroweak sector. So you have to also take into account this in the electroweak for the BSM, for the signal itself. People just started to do it, but you can also do it in a different way. You can see it as a problem or a leverage to new physics again, because if you remember, there was this diagram here, and I told you, to do this, I use, I can write it like some large logs times the matrix element that I have here. So now imagine that you have new physics that is entering only in this interaction, but not in this one, okay? But the logs are large. This means that electroweak correction are giving you sensitivity to new physics for a process that is not the one that you are in principle targeting. So you can see as a problem, but also like a resource to have more information for new physics. And all these things has to be explored. So there is plenty of studies that can be done, and I think it's really exciting, this field at the moment. And I'm done. Yeah.
Don't you want to know when to use minus 100%?
Sorry?
Maybe. Can you give us a quick way one should be worried before doing these calculations in detail?
For the minus 100%.
Yeah,
I mean,
how do I know that I'm running against a wall?
Well, I mean, if you are at 10 TV and you are doing process with W Z bosons, it's likely you get it, because the point is that these logs, okay, they depend on the kinematic, and these are the same for all the processes, but they also depend on the prefactor that are in front of it. So how large is the electroweak interaction of the particle, and the one that is having the largest effect is the Z, but also in WW you see this effect, because I think I have the PT, for example, here of the W, and let me see, no, this PT of WW, I forgot, I put the wrong, okay. So I think here again you see it. Here there is, like, for example, in the Mumu to WW, and you look at the PT of the W, it's not the Z, but still in the last bin, this is dropping down incredibly at 10 TV, and it's telling you that you have a negative cross section.
So the quantity that makes the difference is the leptonic coupling of the Z versus the one of the W, or something else?
No, it's the gauge boson, the coupling of the gauge boson with the W.
The
Casimir, because in front of the double logs there is the electroweak Casimir, and for the one for the Z and the W are the largest, and so it's leading you to the largest effects. So this is something that has to be taken into account, and it's not easy also to do it in automatic. I mean, there are, for example, in MATGraph we automated these effects. There are also others. I think this has been done in Sherpa to these simulations, but for the muon collider purpose, there has been a few studies. Then I have also to add another thing that I could not go into details. I showed that for this distribution and a low electroweak and this pseudo approximation works very, very well. It's not true for all processes, all distribution. Okay, so for example, there are some cases in which you need to go to the NLO electroweak and only the pseudo can give you wrong results.
Yeah, no, my question was related to this. So you said that now you noticed that your expansion was not enough because you saw that you were getting a negative cross section. So that was, of course, a big red flag. And so you fixed it, like going to the next order. But how do you know? So when do you know that it's enough to stop your expansion? Like, how do you know that this next order is good enough?
Well,
and that this result is actually...
No, I mean, the point is that the results that I've shown you, I mean, someone that is doing a resummation, I think would jump from the chair if I said that this is a resummation because it's just exponentiation. Okay, what has been done here, you take the logs that you have an error through week and you do the exponentiation. Doing the exponentiation, you get correctly the log that are alpha to the n log to n. So for example, alpha log squared, alpha squared log to the fourth. Okay. And so your question, if I understand correctly, is when I know that it's enough to take this one and I don't have to do the full resummation. Well, if you want to look at just a double log, this is very easy because you can do the expansion here and you see it. And for example, one thing that we have seen is that for the case here, we have, I don't have the plots unfortunately because I didn't put in the slide, but for example, at 10 TV, for the PT of the top and the PT of the W, the situation is different because here you don't have negative cross section. So if you take, if you don't have a negative cross section, it doesn't mean that you don't need higher log for the precision. Okay, but since they're not so large, in TT bar, it's enough to take this log because obviously you see they're scaling much faster. So if you go to the next log, that is alpha to the third log to the sixth, it will be sub% level. So you actually don't need to do full resummation, you just to calculate the log at the next order. The problem is when you have instead a quantity that is of order 1, because if a quantity is of order 1, you have to resum it. You cannot. So an important point, I think, is having separately the calculation at the NLO electroweak and just the calculation of the log, so that you know how much of your NLO electroweak calculation is really coming from the Sudakov log. Because the Sudakov log, you know how to resum them. The full NLO electroweak, no. So you have to know if these large negative cross section are coming from the log or from other effects. For example, jet veto or other things. That,
Yeah, but maybe I didn't understand. But if you have the full NLO electroweak, then you don't need to approximate the,
no, you need it because you have to resum only the log, not all the quantity. Because you see, the point is that you resum the log, not the finite part. So if you want to do a precise prediction, it's like if you do a simulation at LHC that is an LOQCD matched with shower. The shower is resumming the leading log, is not resumming the NLO. Okay, so you have to match them. Same here, you do your NLO and you resum only the Sudakov log, but to do so you have to know the NLO and separately the log and the finite part and match them.
And you resum both the double and the single logs?
To resum the double and single log, so there's not a a theoretical motivation that you cannot do it, but technically is much more complex. Okay, you need to know all the components that enter in a resummation. Is not a simple exponentiation. So, for example, this is another thing that is interesting for the theory community, that people that are expert in resummation are people not like me that work on electroweak correction, but people that always work in QCD, because this is something that was so SCAT, all this language, it was typically something important for the QCD sector, not for the electroweak part. And now this expertise is becoming necessary also for the electroweak part. And there has been some studies that started to combine these effects. But you see, one thing is doing the plots. Another thing is saying, can you give me a Monte Carlo that is taking into account this resummation effect? I mean, there's things to do before getting to that. There's a lot of work if you want to modeling also with a Monte Carlo correctly these effects. So the challenges are many and interesting. They can be solved. So there's not something that you say this will never be solved, but a lot of work has to be done, and a lot of expertise I think has to be also taken by other sectors to join the force.
Wait. I'm fast, but not so fast.
So just following up on this sort of question. So I understand. So if I compute the next leading order cross section, I get some negative value. So clearly, I understand something is wrong. And now you're saying you just through this resummation, you basically you make this cross section positive. But does it make the number more trustworthy, or it's still kind of?
I think that the result that I'm showing here. So the point of this was not saying I did the resummation. The point of this is saying I need the resummation, because I just did the exponentiation of the double log, and there are also single log that I didn't treat correctly there. So it's more reliable definitely because it's a positive cross section and not a negative cross section. But if you asked me with this simple exponentiation, what is the uncertainty you have there? No, because this is like a toy resummation. This is an exercise that is taking into account the resummation of the double log correctly, is not taking into account the resummation of the other log that I didn't do it, and is not telling you this is the result that you should use. This is just this slide. The purpose of like resummation is important there, and we need to do it in the proper way, not as I did it and I show it to you. And there are people that are also working on there, but it's much more complex to do it just with an exponentiation. But definitely, you have to do it at the next to the leading log. So if you want to have under control the precision.
Okay, so then another question is, as you said, so here in this electroweak processes, the scale is MW instead of like in QCD you get a much larger log than electroweak processes, right? So now when you say, okay, I'm resumming those logs, I'm also wondering what about the non-log term, like say you can have something like constant that is not.
A non-logarithmic term in the
Yes.
electroweak sector.
Yes, because in the QCD, the log are very, very large. So, okay, I'm fine with just throwing away those constant term. But here, should I worry about those terms?
Well, for example, for this, I think that the exercise you have to do is every time, process by process, observable by observable, doing this. So for example, here, the plot that you see here in the bottom, the red is the difference between the pseudolog log and the exact NLO electroweak. So this is plotting the non-logarithmic terms, okay? So here you see that these effects here are of the order of below 5% here. Same was here, and same was here up to the point in which you get this kinematic range, kinematic endpoint. So to do this, what do you can do? You can calculate exactly NLO electroweak. You can do it. You see how big they are, and depending what is your target, you know if you have to take it into account or not. But my impression is that if you want to do precision physics, for example, for the processes here in the left, which you have 10 to the 5 or 10 to the 7 events per bin, probably you need a precision that is not only the NLO electroweak. You need next to reading order electroweak. So definitely, the higher you go in the precision, the more are important all of these effects. But this is another step in the technology, the calculation of two loop amplitudes at the electroweak level. We are not there. There is another technology that I'm not really an expert, but this is an entire different world, amplitudes. So calculation of the amplitudes is a very, very, very complex task.
So when do you treat the W boson as if it comes from a PDF? How do you deal with the fact that the W boson has a mass? I mean, because normally in a proton, everything is massless, right? So how do you...
That's a problem. That's a problem because, I mean, in the description of the PDF itself, you can, in principle, neglect the mass in the sense you keep only the logarithmic term, but in fact then the version also that they've written of the EWA are some simplification because there are also some power correction with the mass of the W. The real problem is the matrix element then you plug in, because you have then to put the mass of the W, because in QCD if you put the mass of the fermion equal to 0, your strong interaction are alpha S is not directly dependent on the mass of the fermion. While in the electroweak sector, if you do a simulation in which you put the mass of the W equal to 0, this is disrupting all your electroweak coupling. Okay, so the things you can do is saying, I work with the idea that the mass are negligible because we are at high energy, but you have to put them inside because otherwise the matrix element are they cannot, you know, the coupling and the masses are related, so it's a problem.
Okay, thanks.
I'm sure there are other questions that can arise, but in the interest of time, we have to close it here. Thanking again Davide for the talk.